Good morning. My name is Jean Marshall. I'm going to talk about our project in smart and sustainable coatings. As part of this project, we have researched the current state of the art in this field along with future developments, and we have also looked at business engagement with this topic as well. So just to give you an idea of the experience in our team, between our team and WMG and also our colleagues at the University of Exeter, we have a breadth of understanding and knowledge in both polymer science and material science, but also in innovation and business engagement as well. So as most of this audience will be aware, in transport applications, quite a lot of components are made from composite materials, and these often undergo finishing processes for either aesthetic or protective reasons. However, when a component comes to the end of its useful life and needs to be recycled, we need to take the whole material system into account, not just what the main body of the component is made of. Coatings can actually limit the recyclability of components by creating mixed waste streams. One particularly important example of that is if the component itself is thermoplastic, then it can be reshaped, remolded, recycled when it's heated up. But if the coating is thermoset, in other words, it doesn't change its shape when heated, then that creates a mixed waste stream and can limit the recyclability of even a thermoplastic recyclable component. So a lot of large suppliers of raw materials for coatings have realized that sustainability is an issue, and various developments have been made over the last sort of few years, couple of decades, in terms of trying to make coatings more sustainable. For example, things like UV curable coatings that don't require volatile solvents in there, replacing volatile solvents with water-based formulations, trying to replace traditional synthetic resins with biological derived resins for binders, this kind of thing. In the future, sort of slightly more futuristic ideas may include things like trying to make your component so that it doesn't need a coating, trying to change the material formulations even more, or possibly even manipulating the surface so that, for example, surface roughness gives you an aesthetic effect rather than having to use a coating. Alternatively, coatings could become stick-on so that there's no energy-intensive process involved with recycling them. Now, as I mentioned, currently the trend in components is away from thermosets and towards thermoplastics. Thermosets do have advantages, however. They can be more robust, more scratch resistant. And so over the last few years, a lot of people have become interested in this technology called vitrimers, which can combine virtues of both. And I will discuss that a little bit more in a moment. But this isn't just an academic interest, and it is becoming commercialized, increasingly commercialized in the last couple of years. So what's a vitrimer? I think it can be thought of as a cross-linked polymer network, which has bonds that can exchange, can break and reform when the temperature becomes high enough. So at the working temperature of the component, the material behaves like a thermoset and is robust and strong. But when it's heated above a certain temperature, then it gains some thermoplasticity. It can be remolded and recycled. So just to give you an idea of the interest in these materials, this graph shows the results of a SciFinder search on the keyword vitrimer, and you can see that, and the results are grouped by date. You can see that in the last 3 or 4 years, then the number of academic articles and patents on vitrimers has actually increased quite a bit. The arrows on the diagram give an indication of when certain sectors started to show an interest in commercializing this technology. And one to watch may be the US startup company Melinda, which just secured a large investment from SABIC recently to develop vitrimers with a particular focus on the automotive industry. However, once you've invented a sustainable or recyclable component, it's not enough to invent such a material and then assume that it will automatically be recycled. You need the infrastructure in place to ensure that it is recycled. And in order to efficiently use raw materials, there needs to be processes in place to look at extending component life where possible, reusing components when possible, but then actually recycling the materials afterwards, which even in the case of a bitumen material is going to may mean separating the coating from the, uh, the component, or if the bitumen is sufficiently um, well, thermoplastic, it may be possible to recycle them together, but then you end up with a mixed waste stream. And there has to be a sort of some focus on second life for those materials. So as part of this work, we've also spoken to various business partners across transport sectors and identified some common challenges in using sustainable coatings, such as finding good second uses for these kind of materials, low value material, because obviously if you try and reclaim a material from a coating, you only get a small amount, so it can become economic to do the recycling. But there are also further specific challenges identified by some industries, such as whether or not customers themselves are actually interested in the sustainability of their coatings. So that's been interesting to find out the specific challenges there. And just to quickly finish, these, just to summarize some of the outputs that we've created across this project, we have a couple of papers that are currently in preparation and will be submitted soon. We've submitted a few bids for further funding to develop this work, participated in some research development programs. We would like to acknowledge UKRI, EPSRC and the Circular Economy Network in Transport for funding this work, and also to thank industrial partners who've given their time to speak with us. And thank you for your attention.